snaps. So what will be tension at the time of snap? And this is to snap. This snaps. So what will be tension at the time of snap? Very simple question to begin with. And then I'm to upscale it. What will be tension at the time of snap? Just at the time of snap. Suggest me way forward.
Well, initially the tension would have to be mg by 2 to balance the weight of the rod.
Correct.
And the moment you snap it,
Mhm.
well, just one second.
Sure.
Yeah, sorry about that. Okay, so if you snap the rod, mg will still be acting downwards,
Correct.
and so I presume tension will not remain mg by 2 at this point, because
Right.
the rod will accelerate downwards. The center of mass will accelerate
Mhm.
downwards, so it can't exactly balance out.
Mhm.
Maybe what we can do is find the instantaneous angular acceleration of the rod about that point, which I presume it will not rotate about the point at which it is attached to the first string.
Do is this, right?
Yes, so we can find its angular acceleration about that point, and from there we can calculate t.
Okay. So angular acceleration be you at any point on the body will remain, correct?
Yeah.
That remains. You can assume it to be alpha. Let's say, as suggested, I assume it to be alpha, alpha being the angular acceleration. So you are suggesting two equations, presumably one being Newton's second law of motion, right?
Yes.
Which is to say mg minus t is equal to m into a, let's say downward, this is ax, this ay for center of mass, so m into ay, right?
Yes.
Okay, one done. What about the second one? You want to write from this position, is it?
Yes.
If you want to write from that position, Vasudev, then you will have to first ensure that there is nothing which is to inflict due to pseudo action. I want to immune my case with the effect that pseudo force can produce. So, how can you help me immune it?
So
If that point is having an acceleration, I don't have a choice. I'll have to take into account pseudo force. So, are you of the opinion this point will not have any acceleration at the time of snap?
mm, well, yes, because it is constrained to move in the vertical direction by the string and can't exactly move left or right because there's no horizontal force. So that would
Mhm.
imply it's stationary, right?
So this point remains. This point doesn't move, right?
Yes. I mean,
Okay. Let me counter or produce, try to protest your point by stating that I am over here. I'm at center of mass. Rod is rotating at an angular acceleration alpha.
mhm.
If I mark this point small a or capital A, just not to get this camouflaged. So capital A and write acceleration of capital A with respect to Earth. Then I have acceleration of capital A with respect to center in addition with acceleration of center with respect to Earth, right, dear? The relative equation, correct?
Yes. Yep.
So acceleration of A with respect to center, if I'm at C looking at A, I'll see it to be moving with an acceleration alpha L by 2, L being the length of the rod in the direction upwards, right?
Yes.
Okay. Going by this frame, let me mark it minus J, okay?
Yes.
So alpha L by 2 in the direction minus J. And what do you say about acceleration of C with respect to Earth, center with respect to Earth? Will it have any acceleration?
Yes. So mg minus t by m.
Mg minus G, right?
Yeah.
Center with respect to Earth will have an acceleration, and that'll be mg in the direction minus j, plus j or minus j.
Minus j.
I have taken minus j upward, right? By this
So,
equation, by this
so I've taken minus.
depiction, I have taken minus
Oh yeah. So okay. Yeah. Sorry. Plus j. Plus j.
plus j.
Hmm.
So mg in the direction plus j. And could you please help me decode it? Help me decipher why will it be mg in the direction j or downwards?
So isn't the okay? The net force acting in the downward direction is mg minus t, correct?
Hmm.
So shouldn't it be mg minus t by m, the
Yeah, that is what
acceleration?
I'm asking. I'm asking.
Hmm.
So it should be mg minus t by m, right?
Yes.
Okay, so minus t by minus because of the reason you know
Yeah.
in m, right?
Yes.
Okay,
Hmm.
and this will be the acceleration of a with respect to Earth, right?
Yes.
Which I presume is not zero, Vasudev. Is it zero?
It doesn't look like it.
Mhm. So
Um.
how you suggest that this point will not have any acceleration? I didn't get that.
Oh, well,
Because if that point is having an acceleration, then I'll have to mark that pseudo force at center of mass and accordingly incorporate it in my torque calculation, right?
yeah, but what I don't understand here is what force is actually causing it to accelerate? Because the only forces acting on the rod are tension and mg.
So there are two perspectives. Either we are missing on this equation or we are not able to extrapolate the situation, right?
One second. So this says it's accelerating essentially. It can't accelerate in the plus j direction, so it has to be accelerating in the minus j direction
Mhm.
because j is the only direction. Is the only it only has a y component.
Mhm. I have one method which may apply to any case you take. Of course, we are to add as per our sagacity, but there is a method which I would be suggesting. Whatever be the orientation of string, this method will help you and will come handy, quite handy. Let's try to figure it out. Instead of initially bugging ourselves with what will be the situation of center of mass, see if you have conversant on this methodology, and if you have laid quite some time, dealt with quite some time, then you'll be able to say at once that this point cannot move in this direction,
Yes.
vertical direction.
Yes.
It cannot move in vertical direction. So at once acceleration, at once we can say the moment is being suggested this problem to get a solution of, we can make a statement and that being this point cannot move in y direction, vertical direction. Therefore acceleration of this point in the vertical direction is ought to be zero.
So okay, so the expression you've written for AE, that's just a method to find tension.
Yeah,
Hmm.
that can be mathematically dealt, but I'm first on what comes intuitively. Intuitively what you can say for sure that this point cannot move along the rod as the rod, sorry, string, as the string is to snap, correct?
Yeah.
So this point can move in a circle, right? That is the only way out.
Yes.
If the string is to maintain its state of taut, then this point can move only on the circular track, right, dear?
Yeah.
So there is no speed initially. If I'm to assume initial speed being zero, there should not be any acceleration in the direction radial. If at all there is one, it can be tangential. Do you concur with it?
Yes, I do.
Okay. In that case, if acceleration in the vertical direction is zero, we can go ahead with Newton's second law of motion, which was any time on mg minus t is equal to m into ay, right? Okay, center of mass. This is center of mass. We assume we don't know. We assume AX. We assume AY. I mean, I'm coming to your point. As you were suggesting, I am supplementing in a way and subscribing to your idea, endorsing it completely. There will not be any AX for center of mass. There cannot be any AX for center of mass. Why so? There is no force on the system in horizontal direction. Mind you, on the system. When I'm referring to motion of center of mass, I'll take all the forces acting on system. So if I take all the forces acting on system, I fail to find any in the horizontal direction, which is what to suggest. It is to suggest that there will be no acceleration of center of mass in horizontal direction, right? Yeah.
Yes, sir.
So AX is zero. AX is zero. Certainly is not AY. AY is mg minus t, right?
Yes.
Okay. This point cannot move in the vertical direction. As you did suggest, let us say alpha is the acceleration instantaneous at the time of snap. Alpha is the acceleration. So if I'm at center of mass, what do I find? I find this point to be moving up. Can we say that?
Yes.
Which is what we have written, alpha L by 2 in which direction? Going by this depiction in the direction minus j. This is what we get to see, right, dear?
Yes.
Okay. We don't know what tension exists, so I mark it as T1. Fine?
Yes.
Okay. Rewriting this equation, mg minus T1 is equal to m into ay. Our first equation, T1. Our first equation rewritten with T1 notation. Next equation, yeah. Now from here, if I'm over here, there is no motion of this point or no possible motion of this point in what direction? In the vertical direction. Horizontal, it cannot move, right?
Yes, so there's no force. Yeah. So,
Yeah. So this point is at rest. Can we say that?
yes, that was my initial argument.
Yeah, that was your initial argument, which we have proved mathematically as well. So what we would say from here, can we write our equation there? No pseudo force.
Yeah.
We are not going to be bugged by pseudo force, no acceleration for this point, neither in x nor in y, correct?
Yes, sir.
My question was at that time, Vasudev, that how can you absolve yourself, how can you exonerate yourself from effect of pseudo force, right? Yeah.
Yeah.
Which is what we have proved. There is no question which is to arise on account of pseudo force because we have cemented our position on this point being at rest at that moment in time when it is snapped, correct?
Yes.
We can write our equation now. Tell me the equation torque about this point. Tension will not produce, mg will produce. So mg into L by 2. Can we write that down?
Yeah.
Is the torque. And that should be equated to
Alpha.
ml squared by 3, right? Into alpha, right?
M squared by 3 times alpha. Yeah.
Okay, so this is our second equation essentially. Can we get T1 from here, dear? Can we write A? Can we write AY also in terms of alpha or the other way around? This point is at rest right there. So what will be AY?
L by 2.
AY can be equated to L by 2 into alpha, right?
Yeah.
Okay, three equations. Presumably we can solve. Please do the needful there. Do me a favor, get me T1 from here at the time of snap.
Just 1 second. I know I did. I'm sorry.
Sure.
Where is equal to alpha? Mm, okay, mg minus t, alright. Then
Yeah.
we get mg minus 3g over 2.
Okay.
It feels a bit odd though.
Yeah, exactly. Is it so? Are you missing somewhere?
Yeah, I think I am. Just 1 second.
Just
Mg
seconds.
minus t1 is equal to may. Mg over 2 is alpha squared 3 by 3 alpha. Oh wait, I forgot to cancel that. Okay, that's completely on me.
Mhm.
Mhm. Okay, 3g over 2l. That's alpha. Yeah. Okay. Mg minus t1 is equal to ml by 2 3g over 2l. Okay, you get mg minus 3 mg over 4. Mg over 4?
Yeah, I think that presumably is the correct equation.
Yes.
So you got the equation and the final answer, right?
Yeah.
Which is mg by 4, right? Yeah.
Yeah.
Okay. Uh, Shy change, not much. This time, the rod, which was taken earlier with vertical arrangement of string, is arranged somehow the way that I'm showing. Okay.
So could you shift the camera a little bit?
Yeah, sure.
Yeah.
This is how it is. We can assume this angle to be theta. This is theta. Let's same angle, theta both the sides. What about tension now? If one snaps, how we should go about this one?
Hmm. Well, mg will still be there, but tension will be acting at an angle. I don't think we can rely on that point being at rest anymore.
Hmm.
So we will
If
have to.
we are, then we'll have to factor in pseudo force, right?
Yeah.
Because this is well within the realm of pseudo force application.
Yeah.
Mhm.
So we
So
will
if
have
you
to.
want to take it into ambit, I don't have any issues, but let's take in a way which is simpler to begin with, right?
Mhm.
Mhm. What we should do? Suggest me, Vasudev.
So we will first have to find the acceleration of that point if we
Mhm.
are
This
in the
point.
pseudo force. No, the point on the left extreme point.
Okay,
Yes.
okay. This one. Okay.
And after that, we can perform the torque balance on the rod and get
Okay.
tension. But we first need to find that acceleration, which I think is the hard part.
Mm, Torque balance. Could you please elaborate on that?
The exact same thing we did last time.
I couldn't get you.
We find all the. I mean, what did we do the last time? That we just we said that that point isn't moving, so we can balance
No,
torque
I
on that
see.
point, right?
But this point will be moving now, right,
Yeah,
Vasudev?
that was my point really. So we have to first find its acceleration, then we can incorporate that in a pseudo force.
Mhm. So how we will find acceleration? This point, you mean to find acceleration, right?
Yes.
That is what you meant. So your argument is stating of acceleration of the point which is remaining, whichever it may be, this or this.
Mm-hmm.
Why shall we discount remaining in this case is this? So of course this point. Why are you not taking center of mass into consideration? During the course of teaching, we have emphasized on motion of center of mass. That was because we are exonerated then from the pseudo force consideration per se.
But that won't directly get us anything. We don't know the tension. We have to find that. Only give us one equation.
Are you to say, am I to learn that because this point being taken, I'll be able to get tension in one stroke?
should write the equations over there. Okay. If we consider from the center of mass,
Mhm.
then whatever tension that is, okay. So mg minus t cos theta is equal to
So,
may.
will you be able to walk me through? Firstly, you said center of mass. That means you're assuming center of mass having some component in this direction and some in this
Yes.
direction, right?
Yeah. So mg minus t
Okay.
cos theta would be may, and
Let me
um,
write that down.
yeah,
Mg minus t cos theta will be may, right? First equation gotten. Yep.
minus t sine theta would be max.
Okay, minus of t sine theta will get us max. Do subscribe. Fine. So far, so good. Weathering it.
Mm, yeah. So where exactly do we go from here?
Alpha you took. The other time you took alpha. This time, no exception. We can take alpha, right?
Yeah, alpha from from which frame exactly? From the frame of that point?
Any point you take, if you're on body, alpha remains, or at center of mass, alpha remains. Correct.
Oh yeah.
It's not center of mass, center of rotation.
Yeah.
Right. Alpha remains. So alpha, if you are taking from this point, then alpha will get us an acceleration of the point which remains in the direction perpendicular to the orientation. That means this direction is assigned to alpha L by 2, right?
So that is if we know it's rotating about the center. How do we know that?
No, no, it is not rotating about center. This is acceleration of this point with respect to center.
Okay.
Okay.
All right. I get what you're saying.
This is A. So with respect to center is what I didn't mention here.
Mm-hmm.
Vector. So assume vector over. Okay. This is what we are getting. That's fine. But what about component of this acceleration? Total acceleration of A, if I'm to write acceleration of A with respect to Earth, you would suggest acceleration of A with respect to center plus acceleration of center with respect to Earth, right? Yeah.
Yes.
So A with respect to center is alpha L by 2 in the direction, let's say minus j cap as per our notations.
Mm-hmm.
And acceleration of center with respect to Earth, we have taken AX in I cap direction and AY in the direction j cap, right?
Yes.
We get what from here? Let us write it down. AY minus alpha L by 2 in the direction j cap plus ax in the direction I cap. Now, acceleration of A with respect to Earth. The other time we wrote this acceleration to be zero, right? A with respect to
Mm-hmm.
Earth, we were in a position to. We can't do this time because this is not the orientation of string. What we can say is in this direction, there will be no acceleration, right?
Yeah.
In this direction, there will be no acceleration till the time string is not getting slack or it is not breaking, it is not getting ruptured. So in this direction, acceleration must be zero, right? Yeah.
Yeah.
In this direction, if it is zero, what do we get from here? Alpha L by 2 cos of the angle theta, the component in this direction of alpha,
Yeah.
or a, or we can write a capital A E component along the string, right?
Yeah.
That is exactly what I'm doing. Component along the string. So this written, and then we are trying to break it in the direction along the string, right? Yeah.
Yes. Sir.
So one is this, which we got. Okay. What about AY, AX? We'll have to break them also in this direction, right?
Yeah.
So AY is in the direction downward. So minus of AY cos of the angle theta. Correct me if I'm wrong. This up, this down,
So,
right?
1 second. Why would that be? AY. Okay.
Uh,
All right. Just 1 second. Shouldn't alpha L by 2 cos theta be negative because you've taken downward to be positive?
I have taken downward to be positive, right?
Yeah.
So alpha L by 2 is negative only. I mentioned minus
That's
J.
not what you've written in the last line.
This
It should
one.
be minus alpha L by 2 cos theta plus AY cos theta.
Correct, correct, correct. Right.
So
Okay,
it
and then this
should
will
be
be plus.
positive.
Right.
Yes. Yeah.
Yeah. And the third one, what about AX positive again
Yeah.
plus AX sine of the angle theta,
Sine
right?
theta. Yeah, sine theta.
Sine of the angle theta, which we are to equate to 0, right? Yeah.
Yep.
Okay. So I think we got the equations from here. This is the third relation which we are getting. We can figure or we can formulate, I would say, a general formula which can be applied for any case, whatever be theta. Can we zero down to a general formula? Can we get tension from here, Vasudev?
We've got. Okay. All right. We can.
Mg minus t cos theta may
Yeah. And then ax.
minus c sin theta max. These were the equation which you got. Then you were in concurrence with the last equation, right?
Yes.
Okay.
Just give me
So
a
I
second
think
to calculate this.
theta is the unknown. Alpha, ax, ay, they are the unknown. Are we in need of one more equation there?
Wait. One
I think
second.
we
Yeah. We do not know ay. We do not know ax, and we do not know theta. And we have three
so
equations.
we can
And
write
we have.
rotational equation about this point to absolve ourselves up again the same pseudo force, correct?
So could you come again?
Can we write rotational equation about this point? A rotational equation about this point. Why this point? Why did I choose this point? I don't want to calculate effect of pseudo force.
So, but that point is accelerating.
Correct, but that is center of mass as well, right?
Oh, yeah. Okay.
Right there.
Yeah.
So it'll help us wish away effect of pseudo force, correct?
Yes.
Let's go by our wish and write torque equation then. What will be torque equation? T cos of the angle theta L by 2, right? About that point.
Yes.
Mg will produce no torque, right there,
Yeah.
is equal to ml square by 12 into alpha. I think this settles now, the last equation,
Yes.
right?
Yeah.
Can we get a formula then for tension here? So as to be an operator.
One second. Can
I
you
want
express alpha in terms of ay and l if you wanted to? Ay.
sure. Ay and alpha are expressed in this direction. Net acceleration must be zero, is what I have gotten right in this direction.
Yeah.
Okay, so that got me this relation, right?
Mm-hmm.
Now, alpha you want to be related with ay, right?
No, there was a pretty simple relation in the previous example. Would that be the case here too?
In the previous example, this one, which one are you referring to?
Yeah,
This
that
one.
one. A is equal to alpha L over two.
Yeah, here it was simple. Why? Because this point was at rest here, right?
Mm-hmm.
So from this point we calculated and accordingly we wrote L by 2 into alpha, right?
Yeah.
Basically here also we did go ahead with the same argument. What argument did I make over here? In this direction, acceleration must be zero.
Yes.
So by that argument, we got this relation, right?
Yes.
Okay. Here we are making the argument along this. So
Mm-hmm.
along this, if I'm to make the argument, I'm getting this relation. I'm not getting that simple relation. I'm getting this relation this time, correct?
Yeah. Okay. All right. I get it. This is like the same relation, but I mean this
Yeah.
analogous to
Yeah.
the relation.
So in this per se, if you mark AX0, you'll get the same, right?
Yeah.
Right. But we are having AX here.
Yeah.
A tad bit calculation,
Yeah.
not much though. Nevertheless, Let's not lose on time. You'll be able to. It'll come somewhere like this. Check out mg
Uh,
cos theta.
ng cos theta. What was that?
4 cos square theta plus sine square theta. 4 cos square theta plus 1 sine square theta.
Okay, I'll figure that out.
Yeah, you can figure that out. And that's what we'll be getting here. You place in the value of theta and you get the final solution,
Hmm.
whichever case it may be, whatever be the orientation. This is what you have to get. So in this case, if I am to place theta, what will be theta? Theta should be given to us. Let's say theta is 45 degree
Hmm.
to make it. The theta 45. Let's check for theta 0 dear. Previous case theta was 0, right?
Yeah,
So theta 0 will get us
mg
how
by 4.
much?
Yeah, same answer as
Right.
well.
Got it?
Yes.
So this will be the equation. Let me ask you on the last one. This is the one. Can you solve it on your own? Can you check this?
Which question? I can only see everything
Spring
starting from 17.
is vertical. Rod is rotated by 45 degree.
Hmm.
Got it?
Yeah.
And ask the same. Let's say acceleration of center of mass of rod.
Hmm.
There are three asks. Acceleration of center of mass of rod, tension in the left string, and acceleration on the lowest point of the rod. Let's start with acceleration center of mass of the rod. How we will go about it? Suggest me something.
And I am assuming the right string is cut.
All right, it's got correct. It's got.
Hmm. Yeah, we could do the same thing we did last time. Write the second law equation, then write the acceleration of that point A. Use that as and solve a system of equations for t, so that we can get the total force.
Can you arrive to the final of any of the three asks?
So, how about I do this on my own time?
Okay, fine. Done.
If you can
Okay.
just send me the picture this way, I'll just take a screenshot. How about that? If you would um, uh, go zoom out a little bit. I mean, I'll take zoom out, so not zoom in. Opposite way.
Okay.
A little bit farther. A little bit more. Yeah. Okay. That's perfect. Perfect. Yeah. Okay. I got it.
Got it?
Yeah.
Okay. So this will get us the empirical formula, and accordingly we can take it forward. Now, Vasudev, a few more points,
Hmm.
uh, which is if is since we are center of mass and you are aware of this question, nothing much. There's a rod, not rod. There's a block, a wedge, which is kept on a pan. Let us say a flat pan or a smooth surface. Okay. There's no friction anywhere.
Hmm.
Normal applied to this system is shown over here, separately shown over here, normal. And total mass of the system being capital M plus small m into G. The system is left to fend for itself. Fine. Normal. This normal is on the system by ground. No friction anywhere, everything being smooth. This as well. The system is let loose. If the system is let loose, then what relation will normal share with m plus m into G?
Hmm. Well, initially, normal is going to be less than m plus m times g, because the center of
Okay.
mass of the system will accelerate downwards as the smaller block slides on the bigger block and comes downwards. But after a certain point, it will become equal to mg. That's
When is
when.
the point?
Hmm?
Yeah, that's when. Sorry. Yeah, please continue.
Yeah, after the small block has reached the ground and both the blocks are moving in opposite directions, normal will be equal
Right.
to the will be equal to m plus m times g.
So till the time it remains, normal will be less than m plus m into G, right?
Yes.
Okay. So based on this argument, I have one more question to share with you again on center of mass. This is a smooth track kept on a smooth surface. There's a block of certain mass which is given Azul to the right. Okay,
Mm-hmm.
capital M. What is the maximum height that this mass will reach? Radius is known of this track. It's part of circle, radius r.
Well, I think the maximum height would be achieved when both of them, both small m and capital M, reach the same velocity.
Mhm.
So,
Will it not leave? If it leaves, uh, let's say this is h.
mhm.
So can you get me the answer in terms of h, capital M, small m, v naught? All the depictions out here being known, let's say. Can we get an answer in terms of these? How will the motion take place? Could you please let me know what we'll see? What exactly we are trying to from here extrapolate should be known to us. Any question that you have taken? Why are we solving that question? So this question will get me an idea on is it possible for this mass small m to leave the track? Certain velocity certainly is required for it to leave the track, right, Vasudev?
Yep.
Let's say we have given it enough to leave the track. Fine.
Mm-hmm.
So if it leaves the track, enough V naught being provided for it to leave the track. In that case, what should be the maximum height attained by small m is being asked.
Okay. So, um, wait, so what you could do
Mhm.
is, all right. So the way I'm seeing this is when you release small m, it's going to push against capital M when it's ascending the slope. So it's going to impart some of its velocity to capital M.
Correct. Correct. Which will happen this point onwards. Right.
Yeah. So
Mhm.
if well, this is usually, I mean, what I think would happen is if the velocity is not sufficient, then both of them would reach equal
Yeah.
velocity at
Then,
some point, and then mass small m would start sliding back.
right. 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 Right.
So
So we
if
kind of periodic motion. We may check on its SHM aspect later. But that's not the case. It's leaving, let's say. It leaves.
okay, so if it leaves, then so wait, my question is, if it's just leaving the track, wouldn't its velocity at the topmost point, vertical velocity, be zero?
Vertical be zero. If it leaves, then there should be some vertical aspect of velocity still to remain with body, right?
And if
Vy.
it just leaves, I mean,
Just leaves means you are to say it's not parting.
yeah, but there's a very fine line between not
Yeah,
parting and
exactly.
parting, right?
Exactly. If I am to assume that that fine line is not to be exceeded, then you may mark it as just part or it remains in touch, right?
Hmm.
Okay. So for me, the case being Vy is zero. At this point in time, let's shift our focus to Vx. What about Vx?
Well, Vx would be, you could just conserve momentum
Mhm.
and find Vx.
So mv naught is the initial, should be equal to capital M plus small m into Vx. That is what you are suggesting, right?
Yeah.
And if it had been this point, then the answer was known to us h, which is certainly not the case. So we are assuming Vy to be not zero here, right?
Hmm.
Let's say Vy isn't zero. Further, please.
I'm having a hard time understanding how Vy cannot be zero.
Why are you hellbent on assuming Vy to be zero?
Because they're asking for the minimum V naught for which it would leave the platform, right?
Minimum V naught? That I didn't ask. I asked for the maximum height it
Oh, sorry,
attains.
I meant to have misheard you then, sorry. I was assuming all this while that if V naught is the minimum such velocity that it leaves, then find the
No, no,
maximum.
no.
Okay, my bad, my bad.
Then of course it will be this point, right? Yeah.
Yeah. Okay.
Yeah.
Um, you can find Vx, and once we've found
Mhm.
Vx, I think we can. conserve kinetic energy, conserve total energy in general to find the vertical velocity.
Okay. So total energy, according to our calculation, will get us half mv naught squared kinetic energy, right?
Mm-hmm.
And then it leaves at this point. It is having Vy. So at this point, what will be the energy? Total height, I don't know what it is. So at total height, what you suggest? What should be the equation of this body? This body is moving. What about kinetic energy of this body? Half capital M into what shall I write?
If you want to consider the situation directly when it reaches its maximum height, then I think it would be simpler, right? So gravitational potential energy would be mg capital H. If
I'll come to small m later. Capital M, what about its energy?
half mvx squared.
Vx square, okay. And then, as you said in this one, we'll take total energy at the maximum height, right? It reaches some height, capital H plus small h. So plus mg capital H plus small h, right? Yeah.
Yeah,
Okay, what else? What about its kinetic energy at the top?
that'll also be just half small mvx squared.
Okay, Vx square. What? This is this equation number two. There are, I presume, three unknowns. So what to do?
Three unknowns. Oh yeah, capital H vx and vy.
What next? It's pretty simple. You'll get it. Get the spunk, please. Come on, play by your hunch, dear.
Oh, so we have conserved momentum, we've conserved energy. What else is there to do? Um,
If you can relate Vy with capital H, it stands
oh
solved.
yeah, yeah, of course, of course. What's the formula? Vy is equal to 2h by g. No, what was that?
Yes, 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 you're right.
Um,
It means with Vy, it is to reach capital H, right, dear?
is equal to 2gh.
Vy square is equal to 2gh.
Yes, 2gh. Yes.
Okay, gotten.
So yeah, I think that should solve it. We have only two variables now, vx and h.
We'll be able to figure it out, right?
Yes.
Tell me, how will the body move, dear? How will small m move after of part?
Parabolic.
How will it parabolic? Okay, it moves in a parabolic sense. Will it be able to get back to this track?
Well, yes, actually, yeah, it will. It
Yeah,
will
and
keep the
where
same
will it?
horizontal velocity.
Yeah, and land at the same position from where it did leave in the vertical sense, right?
Yes.
Okay, so it lands. There's an extension of Iredov question. How will it leave and where will it land? So it'll be moving in a parabolic manner, landing at the same place in the vertical sense, right?
Yeah.
Okay. Slight inkling on what we'll be taking next, Vasudev. One was the optics part, because I'll be taking diversions and not be solo a track. There'll be few diversions which I'll be adding for you to try grow your brain on those, because these are of import to us. First one being what we did in class, if you can recollect, and that being what will be the displacement of an object when the angle is not small. It's not paraxial ray when we are dealing with, rather it's some absolute value which cannot be negated, wherein we cannot assume tan theta equal to theta or sine theta equal to theta, cos theta equal to 1. We solved this. So I would wish you to reflect on the answer which we got there. And one more very important question, and that question, I think I would make you write that question, which is on electromagnetic behavior. So are you through the electromagnetic part, induction part, let's say?
Yeah.
So if you are through the induction part, I have one question. But before of getting you that question, if you have anything to ask over here on what we dealt, the small part that we have dealt with, then I'm all ears to your ask.
No, I got everything.
Okay. So the question which I do have, Asudev, goes, write down, please. This is ITJ. This is ITJ question. This is you can take a screenshot. Why to write this one?
Is it too close? A little farther.
More?
Yeah, I can't see all the options.
Okay.
Yeah. All right. That should do it. Yeah, done.